In previous videos, we developed the energy balance equation for closed batch systems. In this video, we're going to focus on deriving the energy balance equation for a steady-state open system. And I want to emphasize by open system, what I mean is we're going to deal with a process in which we have mass flow rate streams, crossing the system boundaries during the operation of the process. So for this derivation, let's consider the following process. We have a chemical species 1, or chemical species that is fed into the process in stream 1. So it has some sort of mass flow rate associated with it, and the stream is at a temperature and pressure 1, respectively. The chemical species goes into a tank where it's mixed by this impeller here. All right? The species is mixed, and then it comes out of the tank here in stream 2, where it has some mass flow rate and also temperature and pressure associated with it. I'll say that the temperature of stream 2 is greater than the temperature of stream 1, and then also the pressure of stream 1 is greater than the pressure of stream 2. Okay? And so that helps drive the fluid through the process. And so those are the sort of typical things that were defined before in various processes. I also want to mention that stream 1 and stream 2 are also going to have energies associated with them. So stream 1, I'll say, has energy 1 in it, and stream 2 has energy 2. We'll go into more detail about what those mean later. Now for this derivation, before I go through it, I also want to define one more thing for you. One trick we're going to go back, or we're going to use quite a bit in this derivation, is we're going to invoke specific properties. Okay? And so what I mean by a specific property is that it's just a variable divided by or normalized by a mass. All right? And so one example of a specific property that you've already seen in this course is specific volume, right? Which was just the volume of a system divided by a mass. And that gave you units of, milliliter per gram, or something like that, right? So that's one example of a specific property. Another one we're going to use quite a bit is the specific internal energy, right? And so this is just going to be an internal energy divided by mass. All right, and this is going to give us units of joules per gram. All right, so we're going to use this sort of principle quite a bit in this derivation. In any case, before I even get to the energy balance, I first need to figure out how these two mass flow rates relate to each other. To determine that, I'm going to go through the material balance for this system. All right? And so in this material balance equation, I have accumulation is equal to input minus output plus generation minus consumption. I'm now going to simplify this material balance equation based on what I know about this process. So this process is steady state. So I'm going to get rid of the accumulation term. I also know that this process, that there's no reaction going on. So I don't need to worry about the generation or consumption term. And so what I'm left with is just input minus output is equal to 0, or otherwise the input is equal to the output. All right. For the input to my stream, I know it's just equal to the mass flow rate 1, and the output is equal to mass flow rate 2. So what I have now is that the M1 is equal to M2. Let's now proceed to the energy balance. All right. And so our energy balance is structured in a similar manner, where we have accumulation on the left-hand side. And now we need to look at, the difference between the energy in the second stream minus the energy in the first stream. Okay? So that's just what the accumulation is. So on this left-hand side, we're looking at E2 minus E1. On the right-hand side, though, we're going to be looking at the energy transfer terms. Q dot, or the heat, and the work. And because we're dealing with an open system, we're now dealing with a heat rate and also a work rate. Alright, and so now at this point I could start simplifying terms that don't matter in their energy balance. And because we're working with a steady state system, I know that our accumulation term is going to be equal to 0. But that's basically all we could simplify. So at this point I now want to go into detail about what each of these terms are. Alright, so for E2, this is going to be represented by the various forms of energy that exist in stream 2. Alright? And so the different types of energies we need to consider are the internal energy, and there's a dot there, the kinetic energy, and the potential energy. I'm now going to write the functional forms for the kinetic and potential energy, but I'm going to leave the internal energy just like this for now. In any case, the kinetic energy is mass times velocity squared divided by 2, and the potential energy is mass times gravity divided by gc times its height, z2. Alright, so those are the typical things. Now for the internal energy, or I'll point out that in the kinetic energy terms, I have this mass flow rate. For the internal energy, what I could do is I could rewrite it in the same way if I invoke that specific property principle that I talked about earlier. So what I'm going to do is I'm going to rewrite U2 as the mass flow rate times the specific internal energy. All right? So that now when I write my total energy term, what I could do is I could pull out the mass flow rate terms here. And now what I have in these parentheses is just the specific internal energy plus the velocity squared over 2 plus gravity times the height of the stream. I could do the same sort of thing with stream 1, where I have a specific internal energy and also the kinetic and potential energy terms. Alright. So that's what we'll define, or that's what we're going to plug into E2 and E1 here. For the heat term, I'm just going to leave it as is. It's just going to be Q dot. For the work term, though, we could go into more detail about this. So in our system, our work term is going to be comprised of 2 contributions. The first contribution is going to come from what we call shaft work. And that's because if we go back to our diagram, we have to remember that inside the tank we have this impeller here. Right? The impeller is spinning around and it's mixing the chemical species and it's giving it energy. Alright? And so the shaft work is going to come from the impeller mixing. The second work contribution that we need to consider is what we call the flow work. Right, and this comes from the fact that the pressure difference in the system, P1 is greater than P2, that's what's driving the flow of the chemical species through the process. And because the pressure is higher on one side than the other, this pushes the fluid through the tank. And basically, the amount of energy that's consumed in pushing the fluid through the tank, that is what we call flow work. All right. So I'll circle this here and say flow work caused by pressure pushing liquid through a tank. Okay? The shaft work magnitude is going to be determined by things that are external to the process. You know, the size of the motor that's turning the impeller, things like that. But the flow work, that's going to be determined from the streams themselves, specifically the pressure and the volumetric flow rate of the stream. All right. And so as an aside, I want to at least define mathematically how we could describe the flow work. And so in general, if we have a process with j number of streams, so some arbitrary number of streams, our flow work is going to be calculated by the product sum of the pressure times the volumetric flow rate of a stream going into the process, so input. And we're going to subtract off of that same product, but now from the output of the stream. All right? And I want to emphasize here that what we're looking at is input minus output. All right? So you need to pay attention to the order. All right? And that's because the work term in our energy balance is on the right-hand side. All right? All right, so we have volumetric flow rate in our flow work term, but in the process above, I didn't use volumetric flow rate. I used mass flow rates, right? And so we could recast this flow work equation in terms of mass flow rates if I just invoke the specific property principle again, where I say the volumetric flow rate is going to just be equal to the mass flow rate times the specific volume. All right. So by doing that, I now can say that our flow work is equal to the product sum of the mass flow rate times the pressure times the specific volume minus the output version of that product. Okay? Alright, so we're going to apply this form of the flow work into our energy balance equation. Now that we have a mathematical form for our flow work, let's return to our energy balance and start plugging in for E2, E1, and the work term. All right, and so going back to the energy balance. All right, so let's plug in for E2, and we have this. Y2 plus G over GC Z2, and then we're subtracting off the E1 term. U1 squared divided by 2 plus G Z1. Alright, and then on the right hand side we're going to have our heat term, and then plus our work term, which includes shaft work, plus the flow work term. Alright, and so our input to the stream, or input to the process, is stream 1, and our output is stream 2. P2 V2 hat. Okay, and I want to emphasize the order here. On the left hand side we have stream 2 stuff minus stream 1, but on the right hand side we have stream 1 minus stream 2, right? And so the reason for that is going back to even the previous videos. On the left hand side we deal with, finest minus initial, or output minus input, but on the right hand side we have input minus output. Okay, so that's what I mean when I say pay attention to the order. In any case, what we're going to do now is we're now going to move all the flow work stuff to the left hand side. Alright, and so by doing that, what we now have is M2 plus P2 should be hats here. V2 hat divided by 2 plus G over GC Z2 minus M1 U1 hat plus P1 V1 hat plus u1 squared divided by 2 z1. Alright? And that's going to be equal to Q plus shaft work. Alright? Now, that's a lot to write each time. And so what I'm going to do now is I'm going to shorten the left-hand side of the equation. And that's because this internal energy plus P2 V2 term over here, we could redefine this as something called the specific enthalpy. Alright, specific enthalpy. You may have heard about this term before, right? And I'll go into detail about what it is in the next video. But for now, I'm just going to use it as a way to simplify the math. Alright, so we're going to say that anytime we have internal energy plus pressure and volume is going to be equal to enthalpy. So we have it in the here, and we also have it here. So in this part, I could call this specific enthalpy of stream 1. Alright? And so now we've defined a new variable. So now that I have this enthalpy term in our equation, what I'm going to do now is I'm going to reorganize the left-hand side of the equation so that I combine all the enthalpy terms into one parentheses, and then all the kinetic energy terms into another parentheses, and then all the potential energy terms into another parentheses. Alright? So what I'll do here is I'll multiply out the mass flow rates across the parentheses, so for both M2 and M1, and then group things in similar categories. So I'll kind of skip over all the algebra. I'll leave it for you to do that, but I'll write the final result. And so what we're going to have is M2 times H2 hat minus M1 H2 hat, or H1 hat, sorry. Okay, so that's the enthalpy term. And then in the next parentheses, I'll have the kinetic energies. And in the third parentheses, I will have the potential energies. Right? And then that's the left-hand side. And the right-hand side, I just have Q dot plus shaft work. Alright? And so now that I have output minus input here, what I could say is that all the stuff in this parentheses is just what I'll call delta H. Everything in here is what I'll call delta EK, and everything here is going to be delta EP. So that when I rewrite this equation, what I have for my energy balance for an open system is just delta H plus delta EK plus delta EP is equal to Q dot plus shaft work. Alright? And so all that work just to get this very simple and elegant equation. Okay? Alright, and so what we derived here is the energy balance for an open system. It's a very important equation. And because it's so important, what I'll tell you is that you need to write this for any homework problems, quiz problems, and exam problems you encounter which involve open systems. Alright? Now, you'll kind of notice that this equation that we derived here is somewhat similar to the closed balance, or the closed system energy balance we derived in the previous video. But the main differences are on the left-hand side, instead of having a delta U, we have a delta H, right? Because now we're dealing, and this delta H combines internal energy and our flow work terms, right? So that's the first difference on the left-hand side. On the right-hand side here, what we have is just, instead of just having a general work term, we only have the shaft work on the right-hand side. Okay? And the reason we only have shaft work on the right-hand side is because we move the flow work to the left-hand side here for the in order to create that specific enthalpy term. I will say that if you had some other forms of energy in the system, so for instance electrical work, or even let's say the system boundary sizes are changing, you would put them on the right hand side here. Okay?